Welcome to this explainer. Today, we're zooming way in to look at the origin of charge in soil colloids. I know, it might sound incredibly granular at first, literally, but we're going to unpack the fascinating microscopic mechanics that completely dictate how our soil reacts. If you want to understand soil behavior at its absolute most fundamental level, well, it all starts right here. Okay, let's dive into this roadmap. We're covering the foundations of reactivity, permanent charge, substitution rules, temporary charge, organic colloids, and finally, colloid charge data. Let's get right to it. Section 1, Foundations of Soil Reactivity. So what actually makes soil reactive in the first place? According to our source material, it really boils down to two main drivers: surface area, so particle size and shape, and surface charge, which is driven by clay and humus. That charge development, it's intimately associated with those clay-sized particles and humus. To really get how soil reacts, we basically have to figure out where that charge originates. Moving to Section 2, Permanent Charge and Substitution. Now, for inorganic colloids, charge falls into two main camps. Let's look at the first one, the permanent or constant charge. The magic here happens through something called isomorphous substitution. Basically, as rocks and minerals weather over time, cations swap in for silicon, aluminum, and magnesium ions in their respective tetrahedral and octahedral sheets. It's kind of like a giant puzzle. Aluminum, for instance, is just slightly larger than silicon. Because of this, it can slip right into the center of a tetrahedron, taking silicon's place, without actually messing up the crystal structure. This right here is the primary source of both negative and positive charges for silicate clays.
Section 3, Rules of Isomorphous Substitution. So the crucial point is, this isn't just some random free-for-all. There are incredibly strict chemical rules for these swaps. The magic threshold here is 15%. When one ion substitutes for another, its physical dimensions cannot differ by more than 15% from the ion it's replacing. For the swap to actually work, they have to be a close match.
Let's quickly summarize these conditions. First, comparable size, again, within that 15% window. Second, the valency difference between the two ions maxes out at exactly 1 unit. And third, absolutely no disturbing the basic crystal lattice structure. Because these substitutions happen so incredibly slowly over ancient weathering cycles, they are pretty much locked in. That's exactly why they're called constant or permanent charges. They are baked permanently into the chemical composition of the silicate clays. Now, let's look at what usually happens. In a tetrahedral sheet, if aluminum substitutes for silicon, you get a net negative charge. Same thing in an octahedral sheet. If magnesium swaps in for aluminum, that also leads to a net negative charge. But actually, scratch that. It can go the other way too. If an aluminum ion substitutes for a magnesium ion, you get a net positive charge. We actually see this characteristic play out in the trioctahedral sheets of some vermiculites and chlorides. But here is the absolutely key takeaway. Even though there's scope for both positive and negative charges to develop on silicate clays, the overall net charge is always negative. The negative substitutions just completely overwhelm the positive ones. Section 4, Temporary pH-dependent charges.
Okay, so those were the permanent charges. Now let's shift to the second major category, temporary, variable, or pH-dependent charges. This is what you find on kaolinite, humus, olefin, and iron and aluminum hydroxides. Before we track how these fluctuate, we need a baseline. We call this the ZPC, or zero-point charge. It's a crucial index. Basically, it's the exact pH level where the negative and positive charges of a colloid completely cancel each other out. They're perfectly equal.
Think of this as a sliding scale from that 0 point. The environment's acidity literally manipulates the charge at the exposed edges of the crystals. If the pH drops and gets acidic, protonation happens at those exposed hydroxyl groups, creating a positive charge. On the flip side, if you have a high alkaline pH, you're left with an excess negative charge right there on the colloidal surface.
Let's move to and see how this builds chemically step by step for a high pH environment. Step 1, a high pH environment is introduced. Step 2, the hydrogen of the OH- group on the crystal lattice dissociates. Step 3, that free hydrogen links up with hydroxide ions to form water. And finally, step 4, because that hydrogen just left, a negative charge is left hanging on the colloidal surface. It's a straight-up sequential reaction driven entirely by the ambient pH. So how much does this actually matter? Well, for 1-to-1 type minerals like kaolinite, a massive 50% of their charge is pH dependent. Literally half of their reactivity relies entirely on how acidic the dirt around them is. Now contrast that 50% with 2-1 type minerals like smectites or vermiculite. they only sit at about a 5 to 10% pH-dependent charge. Why such a stark difference? It's all about the physical architecture. This variable charge mostly happens at the edges of the structure. 2,1 minerals have a pretty small edge surface compared to their flat basal plane. But kaolinites, they stack up in the C dimension, which totally maximizes the relative area of their edges. More exposed edges just means more surface groups reacting to the pH.
Section 5. Charge in organic colloids.
We've focused a ton on organic minerals, but what about organic matter? Let's introduce organic colloids. Here, the primary source of charge comes from a slightly different playbook, gaining or losing hydrogen ions from specific surface groups. The heavy lifters here are the hydroxyl, carboxyl, phenolic, and amine functional groups. And just like before, the surrounding soil solution's pH acts like a master switch. It regulates whether these groups protonate or deprotonate, which completely dictates their temporary charge.
Finally, Section 6. Comparing colloid charge data.
And this brilliantly illustrates everything we've been talking about. Look at the stark contrasts here. Montmorillonite, total negative charge of 100, and 95% of that is constant. It's locked in permanently by that isomorphous substitution. Now look at organic matter at the top. Huge, total negative charge of 200, but a whopping 90% of it is variable. Then you have our 1-to-1 mineral, kaolinite, sitting at 95% variable, and down at the bottom, gibbsite and geothite are literally 100% variable. Their entire charge completely depends on the pH. This table perfectly captures just how dynamic soil reactivity really is. Which brings us to a fascinating closing thought. We've seen how ancient weathering cycles slowly lock in these permanent charges, serving as the chemical bedrock of our clay minerals. But if that's the case, how will shifting environmental pH levels continuously redefine the true reactivity of our soils day to day? It highlights this incredible ongoing tug-of-war beneath our feet between a soil's permanent chemical history and its ever-changing temporary environmental conditions. Thanks for tuning into this explainer. I hope it gave you some solid ground on the fascinating microscopic forces shaping our soil.